Welcome, everyone. This is part 5 in our series on natural language inference. We're going to be talking about attention mechanisms. Attention was an important source of innovation in the NLI literature, and of course, it's only grown in prominence since then. Well, let's begin with some guiding ideas. In the context of the NLI problem, we might have an intuition that we just need more connections for a lot of our architectures between the premise and hypothesis, right? Possibly in processing the hypothesis, we just need the model to have some reminders about what the premise actually contained. And whatever summary representation we have of that premise might just not be enough from the point of view of processing the hypothesis and feeding the representation into the classifier layer. Relatedly, there's a persistent intuition in the NLI literature that it's useful to softly align the premise and hypothesis to find corresponding words and phrases between those two texts. It can be difficult to do that at a mechanical level, but attention mechanisms might allow us via our data-driven learning process to find soft connections in the weights for these attention layers between the premise and hypothesis and achieve some of the effects that we would get from a real alignment process. So let's begin with global attention. This is the simplest attention mechanism that you see in the NLI literature, but it's already quite powerful. And as you'll see, it has deep connections with the attention mechanisms in the transformer. So to make this concrete, let's start with a simple example. We have every dog danced as our premise, some poodle danced as our hypothesis, and they're fit together into this chained RNN model for NLI. Now, standardly, what we would do is take this final representation HC as the summary representation for the entire sequence and feed that directly into the classifier. What we're going to do when we add attention mechanisms is instead offer some connections back from this state into the premise states. The way that process gets started is via a series of dot products. So we're going to take our target vector HC and take its dot product with each one of the hidden representations corresponding to tokens in the premise. And that gives us this vector of unnormalized scores, just the dot products. And it's common then to softmax normalize those scores into our attention weights alpha. What we do with alpha is then create our context vector. And the way that happens is that we're going to get a weighted view of all those premise states. Each one, H1, H2, and H3 is weighted by its corresponding attention weight, which is capturing its kind of unnormalized notion of similarity with our target vector HC. And then to get a fixed dimensional version of that, we take the mean, or it could be the sum, of all of those weighted views of the premise. Next, we get our attention combination layer, and there are various ways to do this. One simple one would be to simply concatenate our context vector with our original context target vector HC and feed those through a kind of dense layer of learned parameters. Another perspective kind of similar is to give the context vector and our target vector HC each one their own weights and have an additive combination of those two, and again, feed it through some kind of nonlinearity. And you could think of various other designs for this, and that gives us this attention combination H tilde. And then finally, the classifier layer is a simple dense layer, just as before, except instead of using just HC, we now use this H tilde representation, which incorporates both HC and that kind of weighted mixture of premise states. It might be useful to go through this with some specific numerical values here. So what I've done is just imagine that we have two-dimensional representations for all of these vectors. And you can see what I've done here is kind of ensure that proportionally, every is a lot like this final representation here. And then that kind of similarity drops off as we move through the premise states. And you'll see what happens when we take the dot products here. So the first step gives us the unnormalized scores, and you can see that the highest unnormalized similarity is with the first token, followed by the second, and then the third. The softmax normalization step kind of just flattens out those dot products a little bit, but we get the same proportional ranking with respect to HC. Here's that context vector, and you can see it's just a mean of the weighted values of all of these vectors. And that gives us K. And that K is then fed into this attention combination layer. And you can see in orange here, this is the context vector, 2 dimensions. Down here, we have HC just faithfully repeated. And then this matrix of weights WK is going to give us, in the end, after this nonlinearity, H tilde. And then the classifier is as before. So that's a simple worked example of how these attention mechanisms work. And the idea is that we are kind of fundamentally weighting this target representation HC by its similarity with the previous premise states, but all of them are mixed in, and the influence is kind of proportional to that unnormalized similarity. There are other scoring functions that you could use, of course. We've just done simple dot product up here, but you can also imagine having learned parameters in there or doing concatenation of the learned parameters. This has a kind of bilinear form, and this is just a concatenation of those two states fed through these learned weights. And once you see this kind of design space, you can imagine a lot of other ways in which you could mix in parameters and have different views of this global attention mechanism. We could go one step further here. That was global attention. In word-by-word attention, we're going to have a lot more learned parameters and a lot more connections between the hypothesis back into the premise. So to make this kind of tractable, I picked one pretty simple view of how this could work. And the way we should track these computations is focus on this vector B here, because we're going to move through time. But let's imagine that we've already processed the A state and we will subsequently process the C state. So we're focused on B. And the way we establish these connections is by taking the previous context vector that we created, that's Ka here. We're going to multiply that by repeated copies of the B state, and that's simply so that we get the same dimensionality as we have in the premise over here, where I've simply copied over into a matrix all three of those states. And we have a matrix of learned parameters here and an additive combination of the two followed by a nonlinearity. That's going to give us this M here, which kind of corresponds to the attention weights in the previous global attention mechanisms. We're going to softmax normalize those, and that literally gives us the weights. And you can see that there's some additional parameters in here to create the right dimensionalities. And then finally, we have the context at B. So that's going to be a repeated view of all these premises, weighted by our context vector as before, and then fed through some additional parameters, WA here. And that gives us, as you can see here, the context representation for the state B. When we move to state C, of course, that will be used in the place of A here, and C will go in for all these purple values, and the computation will proceed as before. And in that way, because we have all of these additional learned parameters, we can meaningfully move through the entire sequence, updating our parameters and learning connections from each hypothesis token back into the premise. So it's much more powerful than the previous view, where we had relatively few learned parameters in our attention mechanisms, and therefore we can only really meaningfully connect back from the state that we're going to feed into the classifier. So this is much more expressive. Right, and then once we have done the entire sequence processing, finally, we get the representation for C here as fed through these mechanisms, and that becomes the input to the classifier that we ultimately use. The connection with the transformer should be apparent. This is going to return us back to the global attention mechanism. Recall that for the transformer, we have these sequences of tokens with their positional encodings. That gives us an embedding here. And at that point, we establish a lot of dot product connections. And I showed you in the lecture on the transformer that the mechanisms here are identical to the mechanisms that we used for dot product attention. It's just that in the context of the transformer, we do it from every state to every other state. And then, of course, the computations proceed through subsequent steps in the transformer layer and on through multiple transformer layers potentially. And there are some other variants, right? This is just the beginning of a very large design space for attention mechanisms. Let me just mention a few. We could have local attention. This was actually an early contribution in the context of machine translation. And this would build connections between selected points in the premise and hypothesis based on some possibly a priori notion we have of which things are likely to be important for our problem. Word-by-word attention, as I've said, can be set up in many ways with many more learned parameters. And the classic paper is the one that I'm recommending for reading for this unit, Ruck-Taschel et al., where they do a really pioneering view of this and using even more complex attention mechanisms than I presented under word-by-word attention, but following a lot of the same intuitions, I would say. The attention representation at a time t could be appended to the hidden representation at time t+1. This would give us another way of moving sequentially through the sequence, having meaningful attention at each one of those points, as opposed to the global attention, which would just be for that final state. And then there are other connections even further afield, like, for example, memory networks can be used to address similar issues, and they have similar intuitions behind them as attention mechanisms as applied to the NLI problem. And that's kind of more explicitly drawing on this idea that we might, in late states in processing, need a bit of a reminder about what was in the previous context that we processed.